Hey everyone, my name is Ian Ward, and I'm going to talk today about how Mapbox uses the AWS Edge to deliver fast maps for mobile, cars, and web users around the world. So that's a little bit about me first, actually. I work at Mapbox on the engineering team. I'm on the platform team and the security team, and been there since Mapbox started. And before Mapbox, I worked at the company within which Mapbox was bootstrapped. All in all, I've been working in site reliability and security for the past 13 years or so. There are actually 15 people now from Mapbox at reInvent, and we have a booth. So I encourage you to come by the booth. We love hearing about how other people are using AWS, and we like sharing as well. So come on by. We're excited to talk. So a little bit about this talk. That title was really long. What is the talk actually about? So we use CloudFront, Route 53, and the AWS WAF quite a bit. And the talk is really about not how we configure every single detail about these services, but more about how we think about their use, how we analyze and reanalyze how we're using them. And in order to move our business forward and also do it in a way that's improving reliability and performance and just being efficient about cost. So first I'll give some context about what Mapbox actually is, because some of that is important about what I'll later talk about. And then I'll talk a bit about cost and performance, and then configuration, kind of briefly, and then operations, but the operations section is going to touch on some of the things I touch on in the other two sections. And then at the end, I'll talk about security, and specifically the AWS WAF and how we're using it. So first of all, what is Mapbox? Mapbox is a mapping platform for other businesses as well as developers. It allows we have basically building blocks to let you build a location-based application, or maybe you have an application you need a location component in it. So we offer a lot of different APIs to make that possible. We can go through some examples here. This is Foursquare.com. So they're a social networking site. They've been around for a long time. If you look at their site, you use it to find a place to grab a drink or a meal with friends. And if you look at their site wouldn't really exist without a map. It's a big component of it. So these are map tiles that you're looking at with points of interest on them. And then this is the Weather Channel's mobile app. So the weather company, where they're mapping the atmosphere, they use Mapbox's base map upon which to map the atmosphere. And this is Square, so if you make a payment with Square, you can get the receipt on your mobile phone, and they have a map component in there, and it's kind of you could think of it, maybe one way to think of it is a security feature. It shows where you made that purchase. And so there are over 5,000 different platforms that are using Mapbox in different ways, and they're all over the world, big companies and small companies. So first, it all starts with design and data tools. We have a flagship web application called Mapbox Studio, and this is at mapbox.com/studio, and it lets you build a very custom-looking map, upload data, and style that map according to what's actually in the data, so you can make it look exactly the way you want it to and how you need it to match your application. So we have a bunch of APIs and SDKs that you can use to access those APIs. So we have a JavaScript SDK, we have a Python SDK, mobile SDKs for Android and iOS, and a few others. So let's look at some API requests. These are going to come up later. This is a map tile. So those tiles that you saw on the Foursquare.com site, and this is an example of one of those tiles. This is zoom level 0. So you're looking at a 256 pixel by 256 pixel image. This is a raster image. We also have vector tiles, which are tiles that are rendered on the client side. So in this case, the average size of a tile like this is 8 kilobytes to 25 kilobytes. Kind of varies depending on the detail or what features are actually in the tile. And I'll bring up why that's important later. So if you zoom in, each time you zoom in a zoom level, one tile turns into 4 tiles. And this just keeps going. So by the time you're at zoom level 17, you've got 17 billion tiles. Now, looking at another example API is geocoding. So this is where you put in, like, say, I'm in Las Vegas. It will return back what the longitude is of Las Vegas, or you can do the reverse. Say you're building a mobile app and you want to know where you actually are. You can send the latitude and longitude to the API, and it will return back where you actually are, the point of interest or the place name. And here's another example. Oh, and yeah, those requests are an average of 3 kilobytes on response. And then directions. This is turn-by-turn directions. So provide a starting point and ending point, and you get back turn-by-turn directions. Something that we're really pushing on recently is Mapbox Drive. So this is the idea of not just providing those directions, but also feeding in real-time traffic information and influencing the directions that you get back based on things like real-time traffic. So we have a lot of other APIs as well. You can check them out on the site. And the idea is they just are a tool set to build the location application that you need to build. All of these APIs, something similar with all of them is they have an access token that needs to be passed in the query string. So this access token is used for authentication, making sure you're allowed to make that request, and also things like rate limiting. So I'm going to bring up why this is important a bit later. It's just a JSON web token. And yeah, so a little bit about our traffic. Our API traffic is global. Our customers are all around the world. Their users are all around the world. So this is an idea like our mobile SDK actually sends back anonymous probe information about traffic conditions. And so like this is just a couple of days of like probe information coming back to our endpoints, and for a couple of days we have 95% road coverage. This is several months ago, so I think it's different now, but this is the type of coverage basically showing where the users of our SDK are in the world, and it's similar in a lot of other major cities. So based on that, where's our infrastructure? Our infrastructure is global. We're running so the small dots here are CloudFront, and there are a few missing there. They've added a bunch of regions actually recently. And then the larger dots are where our origins are running. We're running in 6 to 9 origins, depending on the API. And we have over 200 million monthly active users, and we're doing billions of requests a day. So like those tiles I showed you, there's a lot of tiles that make up the world. And so you go to a site like Foursquare.com or another site that consists of a map on the web app, and it loads a lot of tiles. So we just end up doing a lot of requests. So let's get into a little bit about cost and performance, how we think about that. We started in US East 1 when we first started, just in one region. But something that we started with was CloudFront right from the very beginning. It was very easy to turn on, and there were immediate performance and cost benefits to doing that. It's something that you can definitely tune over time, but we just started using it right away. And here's a picture of what our origin looks like. So the requests come in through the client, and they hit Route 53, so they hit like api.mapbox.com. And from there, they'll be routed to the nearest CloudFront edge location. And from there, they'll then go to, we use Route 53's latency-based routing. So they'll go to one of the 9 regions based on whatever is least latent from that location. And then from there, they'll hit the actual region, and there's an elastic load balancer. And then they'll hit our application servers, which are running on EC2, and now we're using ECS, service and tasks. And those will make look-aside cache lookups. We're running Redis on EC2 on the spot market. And from there, we also make database requests to DynamoDB. And then to S3, we have a lot of our geographic, like raw data stored in S3. And a lot of that data actually comes from OpenStreetMap. So if you go to openstreetmap.org, you can sign up. Anybody can create an account there and edit data on this like global base map. And we have a pipeline that we pull in these changes. So let's look at some of our headers here, some of our response headers. You can see we have cache control headers. We have a max age of 12 hours and an S-max age of 7 days in this example request here. This is for a satellite tile. And you can also see a couple other things. We have an e-tag set and a last modified header set. So let's talk about that cache control header setting. So why do we use both a max age and an S-max age? Well, as I said, like a lot of the data in the base map is coming from OpenStreetMap. So we have like systems that try to detect things like validation errors or vandalism. Sometimes, since it's an open community, someone can come in and vandalize the map, or maybe there's just an error that's made. If that somehow sneaks in through our validation systems and gets onto the map, we don't want that object to sit in somebody's browser forever for a very long time, right? So we have a lower max age. And then the S-max age is actually what CloudFront will use. If you set both of these headers, CloudFront will honor the S-max age. So it's the shared cache age. And CloudFront has an invalidation API, and we've had to use that API sometimes in the past. And even for clearing like millions of objects that are in the cache, it's effective at doing that. So that's why we're able to set such a longer S-max age, and that leads to a much better cache hit rate. And I'll talk about how we look at those cache hit rates in a bit. So let's just look at an example here. This is an example of 1 million requests. Say you have an average tile size of 8 kilobytes. If you run one EC2, say you do these 1 million requests in 24 hours, you run one EC2, an M3X large. If you've got an ELB, you have to run maybe a database server. We use DynamoDB, but in this example, I simplified it. So RDS, you run for 24 hours. It's an R3. And then you have to also pay for the requests on the edge. So they go through the edge, the data transfer. All that, to do 1 million requests is $17. If you compare that to if you had a 100% cache hit rate, it would be just $3. So that's an astonishing difference. It's also very difficult to reach a 100% cache hit rate, especially with what we're dealing with billions of tiles. There's a long tail of content. And CloudFront uses an LRU to determine what sits in the cache. Even if you set a 7-day S-max age, that object may not sit in there for 7 days if nobody's requesting it. So, but the closer you can get to that, the closer you're getting to a savings at something like this rate. So if you look back at what our origin actually looks like, it's pretty expensive. It's really expensive compared to CloudFront. So this is why we pay very close attention to our content and also to how cache hit rates are behaving. And I'll touch on a little bit more about how much in detail we look at that in a bit. So getting the caching headers right is also very important for performance. So if you look at we've looked at the average time taken. So CloudFront, they provide access logs, and one of the fields they have in those access logs is the time taken number, and seeing definitely single-digit latency on cache hits on many edges, and maybe on average around 12 milliseconds, looking at a small sample from a given day. But if you compare that to a cache miss, what that request has to do, if it has to go through to the origin, there's latency from the edge to the origin, and then there's latency in the origin. So we have lots of caches. We have application caches. We have caches like the look-aside Redis cache. But if it has to go all the way through there, you're looking at a much worse performance. This is an example. Our APIs are all a little bit different in how they perform. But yeah, the miss is just, this hit here is 96% faster than a miss, and this is an actual example. So another thing is conditional requests. This is something that we definitely didn't start off with right away when we started Mapbox and we started using CloudFront and set up our origin. But conditional requests are the idea that, so somebody's got this object cached in their browser, and the object is expired, okay? But the person goes maybe the next day and they're gonna go look at the same place on the map and they wanna load that, and the browser is going to make a request to CloudFront, and they're gonna say, hey, I got this object, it's expired, but do you have the object, and is what I have actually the latest copy? And so that's a conditional get. And so if you think about what happens there, if you're set up to handle this properly by setting these headers, having an e-tag or last modified date on your content, then CloudFront can handle that. If you don't, then you're going to have to serve a 200. So the thing is that if you do a conditional get, CloudFront will, and it's successful, CloudFront will return not the entire tile back, the map tile, or whatever it is the content is. It will just return the headers back and say, hey, you're good, keep what you have, and show it in the browser. And this is not just between the client and CloudFront, but it's also between CloudFront and the origin. And this is also actually where we saw the most impact when we made adjustments here. But CloudFront can also have the object in its cache. It could be expired. But if you have these headers set properly, CloudFront then can go and make a conditional get back to your origin and say the same thing, have the same conversation, and it will, your origin can send back just the response headers, no data actually in the body. And that's a remarkable savings in terms of transfer costs and maybe even compute costs, depending on how your origin is set up. Maybe you don't have to do like all the full compute. So what does it look like? I actually reran this number 45 minutes ago because it was kind of like didn't pass my blink test here. Like it didn't look right. But I'm looking at just 1 billion conditional gets. If you do 1 billion conditional gets, if you're doing like all those and handling successfully as like not modified, like conditional get 304 responses, it's just $54 in transfer cost using CloudFront's market rate on their website, the pricing that they advertise. But if you have to do all 200s, you're looking at $2,125. It's a huge difference. So getting these set right is definitely worthwhile as you start to do more traffic. So some takeaways about this section are, yeah, definitely like we used this, the CDN from the start. There were clear advantages to doing that. It didn't have a lot of overhead to configure it. But then like, knowing your content, knowing what you need to, what types of cache headers you can set based on what the risks are is important, and then tuning over time. So, that conditional get handling wasn't something I think that we hit until a couple of years after launching the API. But once we hit it, it was super important and definitely goes into how we price things for our service. So a little bit about configuration now. We have now, we started off with just one or two behaviors. We just had one API. We just did maps in the beginning. Now we have a lot of different APIs. We have like about 13 different origins. So we've got directions origin, we've got a geocoding origin, maps origin, and so on. And sometimes these are actually different teams. They're like different teams at Mapbox who manage those origins. And the thing is that these are CloudFront behaviors. A behavior in CloudFront is basically, it's like the router. It says, okay, if this request has /directions in it, send it to the directions origin. So it's really important to get the order of the behaviors correct. So if you have like a less specific match above a more specific match, traffic will never make it to that more specific match. So it's super important that they're in the correct order. So how do you, one of the questions is like, if you have a bunch of teams, and how do you manage this router together? And then not only that, but there are also, like, as you add a behavior here, there are a lot of different options. It's, CloudFront is pretty flexible. Gives you a lot to work with. If you look at the last one there, it's about whether or not to forward the query string. So if you remember, I said all of our API requests require an access token, and that access token is actually in the query string. So if somebody sets up a behavior and they don't set this, check this box or like flip select to use passing the query string back to the origin, then it won't work right. So how do you do this when the options matter and the order matters? Well, does everybody use or has heard of or knows about CloudFormation? So yeah, CloudFormation, it's pretty popular. CloudFormation, just to quickly summarize it, it lets you like write a JSON template, and instead of like going and clicking through the console, the web console to create all of your resources in AWS, you can define them all in a JSON template. It just says, okay, you can define like an auto-scaling group or some EC2s or policies. You can even define a CloudFront distribution. So our CloudFront distribution is in a CloudFormation template. And what this allows us to do is commit that configuration to a GitHub repository. And then we can use things like Travis or CircleCI, some other integration testing. So whenever somebody makes, so say we're creating a new API, and somebody goes in and adds that configuration into the CloudFormation template, like the additional behavior into the CloudFront configuration in that CloudFormation template. If they don't define to pass back the query string, it will fail the tests. So this is a way to kind of like allow a bunch of teams to manage this configuration together. So yeah, some takeaways about this are, yeah, CloudFront just there's a lot of options. It's about, I think, finding ways to manage that complexity. Some things are like, even though you can configure cache control headers in the actual the behavior, you can also set those on your origin. So that's one way. Another way is doing things like testing the actual distribution configuration by using CloudFormation. So now let's get into operations. A lot of what I just talked about is going to come up in different ways in these next two sections. So some of our origins are in 9 different regions. And the way we do this is we use Amazon Route 53 latency-based routing with failover. And so like I was saying, we use CloudFormation for pretty much everything. And so with say like the geocoder or API or like the directions API, each of these APIs, each of these origins will have its own separate, what we call a service stack. So we define all the resources for the geocoder stack in a CloudFormation template. And that'll be like maybe a auto-scaling group, maybe some tasks, a service for ECS. All this is actually in the CloudFormation template, and we use some of CloudFormation's features that let you do deploys, so like cycling instances. We use some of these features in CloudFormation to basically do all of our deployment through the CloudFormation API. And so with our DNS records, we'll have like this is the map, like example of the map stack. So we'll have like this map service stack, but then we'll have a DNS stack, which is like just the DNS entries and the Route 53 health check definitions in a CloudFormation template. And we call that the DNS stack. So these records look like they're all identical, and the only thing that's differing about them in there is the region that they're in. And so like what could go wrong, right? The reason why we're running in 9 regions is not just for performance, but it's also for reliability. But like, yeah, just because you're running in 9 regions doesn't mean nothing's going to go wrong. It means more stuff is going to go wrong because you have more surface area, more stuff deployed, and more probability that something will go wrong. But it's definitely better than something going wrong if you're just in one region. So what kinds of things go wrong? Sometimes it's self-conflicted, like you have a bad deploy. Or maybe like your deployment code, somehow there's a bug in it or something happens and you lose all the capacity in a region. Or maybe it's just that a region is having like a intermittent internet network issues. So say like there's actually an issue happening in EU West 1, so in Ireland. Say there's like an internet outage, and what will happen in our situation here is like the Maps API, the Route 53 health checks, they're checking to see like if the string Mapbox, for example, exists on each of the different endpoints in each region. And so maybe this packet loss is happening in Ireland, causes it to fail over. So like the traffic fails automatically and it goes to US East, so to Virginia, right? And then, but the packet loss is such that it's like not so horrible, and the Route 53 health checkers say, oh, it's looking like it's healthy again. So the traffic goes back. But actually it's not healthy, it's just like intermittent packet loss. So we have like elevated error rates go up again, and then it goes back and forth and back and forth until whatever the problem is gets fixed. And these can last, it doesn't happen every month, but it's happened, and they can happen and last for hours. So yeah, automatic failover is not always such. It doesn't always stick the landing the way you want it to. So the other thing is that manual failover is error prone. So a few of the ways we've dealt with this before is that one way is to go into the console and manually delete the record for EU West 1, the DNS record for the maps endpoint. But that's error prone. You could go in there and actually delete the wrong region and you have 2 problems. And then another thing is that we've tried, we have command line tools that we use to interact with the AWS APIs, and I'll get into that in a bit. But we had like a separate, we have like basically one command line system that we use to interact with CloudFormation. But we built something kind of like outside of this. And so everyone's familiar with this one tool, but we have this like, if you want to do manual failover through this command line tool, you can use this other tool. And even though it had some tests with it and everything, nobody was comfortable with, whenever it came to do the failover, no one was really comfortable with, okay, is this actually going to work if I run this command? And the interface was kind of different. So Yeah, how do you do automated manual failover well? Well, like I said, we do a lot with CloudFormation. There's this open source tool we have called cfnconfig. It's in our GitHub repository. It's Mapbox, github.com/Mapbox/cfnconfig. And what this is, it's a command line tool written in Node.js, and it's essentially a wrapper around the CloudFormation APIs. So you can create, update, delete stacks, all from the command line. Just install it with Node.js. And so to like update the geocoder stack, you would do cfnconfig update geocoder production, and this would like update the actual geocoder EC2s, autoscaling group, whatever it is that's in that stack. But then, okay, so what about failover? We were talking about failover. We've actually, as I said, like we had all of our DNS records also in a separate DNS stack, which is just the records and then the Raba Traffic health checks. So what you can do now is you can go and run cfnconfig update --DNS on the geocoder stack, and it will take you through these prompts. These prompts are actually based on the CloudFormation parameters that are in the template, and it'll say, okay, should I route traffic to US East 1? Yes. You go through until you get to EU West 1. You say no. It will update the CloudFormation stack, and by doing that, there's actually just a condition in this template that says, okay, if somebody sets this to no, tell the health checker in that region to check for failed. And failed doesn't exist. We don't serve that on our endpoint. So after a minute and a half, Route 53 will fail that. But it's great because it's the same interface that anyone uses. Like everyone uses this interface every day to create testing stacks, staging stacks. And so when you're in like a high stress point where you need to do a manual failover, you use the same interface. And this has worked, it just feels natural. Yeah, so the next question is, did it actually work? Did the failover work? When did it kick in? And this is another thing we've done. It's a tool. It's just basically looking at the different places in the console that shows like, okay, what is the region, like in what all regions is this stack configured to run? And like in all of those regions, what is the current health of those regions? Is it configured to be healthy? Or is it configured to be failed over? And then if it is, you can see if it is configured to be failed over, you can see if it's actually failed over yet. So instead of you basically when you're in this high stress moment of wanting to fail this region, you don't want to be like bouncing around to different consoles and whatnot. You want to just do it all in the command line, or all in one spot, right? And this is how you can do it. So other ways to check status. Other things we do to look at our traffic on a hourly or daily basis. We take all of our CloudFront logs and we put them in an Amazon Redshift cluster. So we have like billions of requests a day, and so we have billions of logs. This is why we put them in Redshift. But you could, if you have less or the same, if you have the same, I would put them in Redshift. If you have less, maybe you want to put them in some other type of relational database. But Amazon Redshift is really convenient. I'll show you why. So the log files, CloudFront delivers those to S3, just as compressed log files. And then we have a Lambda that's just running, and whenever those files are delivered, whenever there's enough of them, this Lambda builds a manifest file, and all that is a list of these files. And the reason why we do that is because we have this other EC2 that runs, and it waits for these manifest files to be redelivered onto S3 by the Lambda. And the EC2 takes this manifest file, and Amazon Redshift, it supports doing this copy command. You can actually copy directly from files in S3 into Redshift. There's some great blog posts on the internet about how to do this. But yeah, the idea is that you do this copy command, and all the log file contents will get copied into your Redshift cluster. So once those logs are in there, what do we do? SQL, I've been using it since I first started programming. It's super powerful. I still love it today. It's an old language. It's an old, but it's great. So like, you can look at the CloudFront documentation, see what all the fields are in the access logs, but it's similar to like any other web server. There's some more additional things in there. They're like the Xedge result type. This is actually, was it a cache hit or a miss? So we're looking here at, okay, was it a cache hit or miss? Basically looking at what's our cache hit rate. I'm grouping by cache hit rate here, so I can see the hits, misses, refresh hits. And we have this CloudFront log staging table. So we keep like 48 hours of logs in this Redshift cluster. You can still query that pretty quickly with Redshift, but we also have this staging table, which is just 1 hour of logs. It's the last hour of logs. And so it's like, it gives you a big enough logs to do a quick sample, and it's super fast queries. So other things we can do is like if you have the customer name, if that's part of your URL, or maybe it's the access token, you can do things like, okay, group all the traffic right now by customer. Sometimes we have like these big spikes on the edge, and maybe the spike is on the edge of like a increase in traffic, but it doesn't make it to the origin. And if you don't have a way to like look at what's going on, you're just like, I hope it's legitimate traffic. I'm not sure, but so this is why it's like great to have this at our fingertips. So like if you combine, for example, the last thing I just showed you there, the hit rate, or like the actual, like the edge status, so the result type, whether there's a hit or a miss, combine that with a customer, you can start to look at, okay, is this customer, if you think about like the cost stuff I talked about before, you can start to think about, okay, is this customer costing us a lot of money compared to other customers? And you can start to make business decisions about maybe there are certain types of customers and they have certain type of traffic which is more costly to serve than other customers. And you can start to help like the business team influence how they think about how they should be selling the product. Maybe not all traffic is the same, not all customers are the same. So you want to like look at this and really look at it in detail and understand before going out and getting into a negotiation of like of some new traffic, understanding like what that traffic actually is. So this makes it really possible to look at that. Other things are maybe we have like an incident, maybe we lose an origin, or maybe there's like some people in a part of Europe that are complaining about certain like elevated error rate. So we could do this. We could look at, okay, let's look at the status codes organized by edge location. And let's just look at where the status is like 5 something something. So like all the 500s. And we can see, okay, we have this like failover in EU West 1. What was like the error rates in all the different edges, for example, just to look at kind of like the blast radius of that problem. And that can help us communicate on our status page, for example, about, yeah, we had this problem here, or like these edges had this problem, and this is what the total error rate looked like in the different locations. So yeah, some thoughts here about this this section is, tooling for your manual processes, it makes a lot of sense, and just like, instead of, if we have like 13 different teams at Mapbox, instead of having like 13 different command line interfaces to do similar or the same thing, putting it all into one that you can manage together makes a lot of sense. And you can really get a better honed product that way. And then just learning from your logs. There's a ton to learn from your logs, whether it's for operational purposes, whether it's for business purposes. There's a ton of interesting information in there that can help guide you. And then, so now security. Now that we've talked about logs here, specifically with security, I want to talk about scraping and DDoS. So scraping, if you think about like the world, it's a very discrete thing. It's, as I said, like zoom level 17 is 17 billion tiles. And so we often see like maybe it's somebody who's trying to start the next Mapbox using our IP, or maybe it's a customer, somebody who should be a customer, but they're just trying to like steal the tiles. They write a scraper, something that's going to go and like serially copy, try and download the entire world or a certain zoom level or something, right? And so that's a scraper, and sometimes it looks like a DDoS because sometimes it's done through data centers with hundreds of IP addresses. And what I was talking about there about like having our logs in Redshift, being able to kind of like really see and look and understand your content is important to be able to fingerprint what bad traffic looks like. So like you need to know what your content, like what normal traffic looks like to know whether traffic might be bad. So what can we look at? These aren't all of our secrets, but if you see a lot of traffic coming from a single IP address, that's a pretty good giveaway. But then we have like enterprise customers that we allow to proxy to us, for example. So how do we distinguish between that traffic and like a scraper? There's other things, so is it like an unknown proxy? Other things are like maybe all this traffic is coming from a single IP address and it's got like just one user agent. Often like people don't go through the steps of making the user agent something that changes So like the user agent will be from like Java or like libURL or Python. And so you're like, that looks suspicious. And then other things like irregular content profile. Like as I said, like the average tile size for a map tile is like between 8 and 25 kilobytes. But sometimes we see people doing like lots of requests for ocean tiles or lots of requests for land tiles, just blank tiles. And these tiles, these are like 100 bytes each. So if we see, for example, somebody doing a bunch of traffic from a single or like maybe just a few hundred IP addresses and like their average content size is something like under a kilobyte, that's kind of weird looking. So that helps us make decisions about whether that traffic is legitimate or not. So this is where the AWS WAF comes into play for us. It's a web application firewall. It's very flexible, has a lot of options. It looks like this in terms of like where it fits into your architecture. You've got good users, bad users just coming in from wherever. And the traffic goes through the WAF first. And then from there, it goes onto CloudFront and then onto your origins. And the whole idea is to prevent any unwanted traffic from ever making it back to CloudFront even and back to your origin. So there's a lot of different ways you can block traffic in the WAF. You can do it by whether something matches in the headers. Maybe you can look at the user agent and be like, yeah, if the user agent is Python, block that. But you have to, the question is kind of like, how do you might have customers that are allowed to proxy and allowed to use like scraping based on whatever deal you have with them. So you kind of like, you have to differentiate there. But then the other question is like, how do you update? So how do you update the WAF? If you thought like, I thought like failing out a region was kind of a high stress thing, tedious, but then the WAF, it's very flexible, it has a lot of options. And you go into the WAF and you're like, looking at all the different options and like trying to figure out, okay, I've got this scraper going and it's starting to take down this region because of the amount of traffic it's doing. Or it's like costing us a lot of money, or it's like, scraping or abusing somebody's website. Making a quick decision could end up blocking like all your traffic. So how do you manage this? Well, same thing. We put it in CloudFormation. Our WAF configuration is in a CloudFormation template. But like CloudFormation templates are kind of static, right? It's just like a JSON template. But say one of the most reliable ways we found to block is by IP address because it's very difficult to spoof an IP address, whereas you can easily spoof other things in the request, like the user agent and so on. So something I really love about CFN config is that it can actually not just like take a CloudFormation template and upload it to the API, but that CloudFormation template could be just JSON or it could be JavaScript. So if you look here, this is a JavaScript CloudFormation template. And it's just including this IPs variable, and it's calling libips.js. And all that does is, this is all in a GitHub repo. All that does is it looks at a text file for like a list of IP addresses. And based on what it finds in there, it will explode it later down on line 12 there. You can see, okay, the IP set descriptor. This is supposed to be a long list of IP addresses or a short list, whatever IPs you want to block, right? If you have to go in there and update this by hand on the fly as you're trying to block this traffic, it's not going to work. So you just do CFN config update on this WAF template, and it will look at this list of IP addresses in this text file, which is all version controlled, so we can see what we were blocking, what we're about to block. When you run CFN update, it's going to show you a diff of what it's about to change in the CloudFormation configuration. So it manages all this complexity for you and builds this template on the fly. And we've seen this effective, like the WAF, what's going to happen here actually is the WAF, when you run CFN config update, it's going to upload it to CloudFormation. And CloudFormation is going to go on and reconfigure the WAF for you. So you don't even, nobody has to ever even go into the WAF console and do any clicking or anything. You're going to always block in a known expected way, no matter who's doing it on the team, at what time of day, under whatever circumstances. It's going to be a similar workflow, not as error-prone as an approach where you'd have to go into the console. So yeah, CF and config, it's written in Node.js, but like that pattern there, it's something if you use Java, if you use Python, there are other tools similar to this. It's the idea that just because CloudFormation template has to be JSON doesn't mean you can't write it on the fly with something like JavaScript. And you can even do things like we've done this a couple of times. Haven't always felt great when we had to do it, but you can do like asynchronous calls too. So maybe you build this CloudFormation template by maybe at the top there you have some like calls and you do like an API called AWS and you're like make an API call, you get some resources, and based on the response you get back, then based on that you build your CloudFormation template. You could even do that if it comes to it. The more common pattern we have is just writing it in JavaScript and doing things like looking up from other libraries that are static that we built and building out the CloudFormation template that way. Yeah, so we found the WAF effective at blocking attacks that are coming from single computers, trying to download the whole world, which will take a really long time. Also data centers, hundreds of IP addresses coming from major data centers around the world. The WAF has been effective in blocking in all of those situations. Yeah, so some key points about this are just knowing your content, being familiar with it to know what is good and what is bad, and then having your logs, like the CloudFront logs, in a place that you can use for lots of different purposes, whether it's on the business side, whether it's for day-to-day operations, trying to tune performance and tune maybe the origin and how well it's caching, getting your cache headers right, all the way to security and the WAF, having those logs in an accessible place. We've been in the spot where these logs weren't accessible, and you kind of just are left sitting there with not many options. But having them in a place where you can query them on the fly is super, super helpful. And then just being, specifically with the WAF, just being familiar with what your options are to block, knowing what's going to be most reliable, what you can and can't do, and then building something around like automating being able to do that. Yeah, so just to conclude here, that the talk wasn't really about like how we configure every single thing about all these edge services. It's more about how we think about them, how we use them on a day-to-day basis, and how we distribute that, how to distribute that across the whole team in terms of like making everyone own that and manage that themselves, and how you're using them and the information you can get from them can help to influence other teams, not just the platform team, for example, but the business team or the security team at your company. So yeah, if anyone has any questions, I can take those now.